Water vapor rarely accounts for more than 2% of the atmosphere's total volume, yet this nearly invisible gas operates as a planetary engine. The hydrologic cycle operates as a continuous, closed-loop exchange of thermodynamic energy. When water evaporates from the surface, it pulls heat from its immediate surroundings. The surrounding air cools down, and that thermal energy gets locked inside the rising vapor. This diagram tracks the thermal exchange. Heat enters the water, and vapor rises. When it condenses back into droplets, it releases stored energy as latent heat. This warms the environment, creating updrafts, the primary fuel powering large-scale weather systems like cyclones. Every weather event you experience, whether it is a gentle morning frost or a hurricane, is the local result of this single thermodynamic engine encountering different boundary conditions. The total amount of water in the sky above you has almost zero bearing on whether it will actually rain today. To understand why, we have to define exactly how air holds moisture. This box models absolute humidity. Absolute humidity is the actual physical weight of water vapor contained within a specific unit volume of air, usually measured in grams per cubic meter. Relative humidity operates differently. It is a ratio. It measures the amount of moisture actually present compared to the maximum capacity that parcel of air can hold at its current temperature. As the air heats up, its capacity expands. Notice the physical amount of water hasn't changed, but because the container effectively got larger, the relative humidity percentage plummeted. 3 rules govern this relationship. First, if the temperature stays constant but we introduce more evaporation, relative humidity goes up. Second, if we raise the temperature, the retention capacity expands, forcing relative humidity to go down. Third, if we lower the temperature, the air's retention capacity physically shrinks, squeezing the existing moisture and forcing relative humidity to rise. If the temperature drops far enough, the shrinking capacity eventually hits 100% saturation. We call this exact temperature threshold the dew point. Absolute humidity tells us the exact volume of water available to fall, but relative humidity alone dictates whether the physical limits of the atmosphere will allow that precipitation to form at all. When air hits its dew point directly at the surface of the Earth, the moisture has to go somewhere. It condenses onto whatever solid objects are available. This split diagram illustrates the boundary rules. On the left, the temperature drops to the dew point, but that point remains above freezing. The result is liquid dew forming on low-lying surfaces, providing hydration for plant life. On the right, the dew point threshold is crossed entirely below 0 degrees Celsius. This triggers deposition, a direct phase shift from vapor into solid ice, creating crop-damaging frost. Move slightly off the solid ground and into the lowest few meters of the atmosphere, and the condensed moisture has nothing to cling to. Instead, it remains suspended in the air. We label this suspended condensation as either mist or fog. Physically, they are composed of the exact same water droplets. The distinction is strictly a measure of particle density and human visibility. Fog forms when converging air currents create a dense suspension of droplets that restricts visibility to less than 1 kilometer. Mist is a less concentrated version of the exact same phenomenon. Visibility remains between 1 and 2 kilometers, a condition frequently found on mountain slopes as warm air rises up the incline. A sudden shift in the ambient temperature can force a clear, open stretch of air past its dew point in a matter of seconds, immediately precipitating millions of suspended droplets and dropping visibility to 0. Dew, frost, and fog occupy the exact same physical space in the environment. Their differences are dictated entirely by microscopic shifts in boundary temperatures. Beyond ambient temperature, we categorize dense fog by how the air mass moves. This cross-section shows radiation fog. It is an entirely vertical exchange. After sunset, the ground radiates its stored heat straight up into space. The layer of air touching the soil cools rapidly, reaches saturation, and forms a dense, low-lying blanket. Advection fog relies on horizontal momentum. A warm, highly humid air mass travels sideways over a substantially colder surface, like an ocean current or a snowpack, chilling the bottom layer of the moving air into an opaque fog. These are natural thermodynamic events, but when industrial pollutants intersect with these low-hanging moisture traps, the boundary conditions alter. Industrial smog, or gray smog, occurs when stationary combustion sources like coal power plants pump high concentrations of particulates and sulfur oxides into these trapped, damp air masses. The hazard extends far beyond just poor visibility. Sulfur dioxide readily combines with suspended atmospheric water to synthesize sulfuric acid, which eventually falls back to the earth as acid rain. Photochemical smog, or brown smog, dominates sunny, high-traffic environments rather than heavy industrial zones. It covers expansive land masses, but it requires a specific catalyst to form. This chemical flowchart illustrates the reaction. Ultraviolet solar radiation strikes the nitrogen dioxide and hydrocarbons emitted by vehicle exhaust. The sunlight physically splits the molecules, causing them to recombine into toxic ground-level ozone. Heavy industrialization overrides the atmosphere's natural chemistry. It takes the simple thermodynamic cooling process of water vapor and turns it into a suspended toxic hazard. Leaving the boundary layer, we enter the upper troposphere. Here, condensed droplets form the cloud formations that regulate global weather patterns. Meteorological classification groups these clouds using two rigid criteria: their physical shape and the altitude of their lowest point. This grid maps those 10 basic structures. Below 6,000 feet, we find uniform gray stratus clouds composed of liquid water. Sweep up past 18,000 feet, and the extreme cold dictates thin, wispy cirrus clouds, composed entirely of ice crystals. For these suspended clouds to actually drop precipitation, large volumes of atmospheric air must be driven upward so they can rapidly cool and expand. 3 distinct geographic mechanisms provide this lift. This cross-section shows orographic precipitation. Prevailing winds slam into a mountain range. The air is physically deflected up the slope, chilling until it drops heavy precipitation on the windward side, leaving only dry air to cross the peak. Without mountains, we rely on cyclonic or convectional precipitation. Intense, localized surface heating creates a powerful thermal updraft. As the air skyrockets, it cools, forming towering cumulonimbus clouds characterized by heavy, sudden rainfall. Finally, frontal precipitation occurs when 2 distinct air masses collide. Dense polar cold air acts as a wedge, physically sliding underneath a warmer, lighter air mass and lifting it into the upper atmosphere to condense. The type of storm may vary, but the physics do not. Rainfall requires a mechanism of forced vertical lift and subsequent cooling. These localized rules of relative humidity, thermal lift, and saturation point scale up to dictate the layout of the entire planet. Near the equator, immense solar radiation evaporates vast quantities of ocean water. The extreme heat forces continuous convectional updrafts, pushing the air to total saturation and triggering daily heavy rainfall. The result of this thermodynamic engine running at high capacity is the global equatorial rainforest biome. This map plots that reality. The dark blue equatorial band represents high relative humidity, intense thermal lift, and maximum precipitation. In the tropical high-pressure belts between 25 and 35 degrees latitude, the physics reverse. Descending dry air aggressively suppresses relative humidity. With the air permanently trapped far below its saturation point, precipitation becomes physically impossible, carving out the world's most arid environments. The stark contrasts between lush jungles and barren deserts are not geographic accidents. They are the strict physical manifestations of the troposphere running its thermodynamic equations.